as promised, I wanted to bring you a object in equilibrium 3D problem with the support reactions. And I chose this problem because it has some very interesting things. I don't consider this to be an easy problem at all. But if you've learned the concepts of solving 3D statics in the previous chapters, this shouldn't be an issue as far as the computation, more so like analyzing the support reactions. So I'm going to emphasize that more than the 3D procedure because I'm going to assume that you already know some of those 3D procedures. If you don't, be sure to check my video on that. Okay, so let's start with reading the problem carefully. The smooth uniform rod AB is supported by a ball and socket joint at A, the wall at B, and cable BC. So we have three supports. We have the ball and socket, which is this guy right here, A. We have the wall, obviously, it's the plane YZ, and we have the cable BC. Okay, determine the components of reaction at A, the tension in the cable, and the normal reaction at B if the rod has a mass of 20 kilograms. So the only force that's, well, I should say, the only force that we know in this rod is its own weight. Okay, everything else is an unknown. Okay, and that's why this problem is a little bit tricky because we're literally gonna use every single possible equation to solve this problem. So before we get to it, I'd recommend you to draw a free body diagram. In my case, I'm going to cheat a little bit and just draw on top of the picture just because I think it will be better for you to visualize some of this. So my free body diagram is obviously rod AB. Then I'm going to cut this cable BC and I'm going to have a tension force here, which I would just call TBC. And the reason why I drew it going that way is because it's a cable. That's the only way that a force through a cable can go. It has to go in tension, right? I couldn't have drawn it the other way around. That would be wrong and would lead to the wrong answer. Okay? Then we obviously have the weight, which I'm going to draw like this at the center. That's how you should draw it. So we have the weight, which is unknown, and I'll calculate that in a second. And then we have the supports at A and the force at B from the wall. So to discuss that a little bit, first let's talk about the wall. So the wall, let me just, kind of like draw it in perspective here. So the rod is leading right at point B, right? It's leaning, I'm sorry. Every time you have a surface contact, the force that surface is doing should be perpendicular to that surface. So in that case, perpendicular to the YZ plane, this and which they call and B, I think, normal B is going to be normal to the YZ plane. In other words, in the X direction. So NB is going to be going that way. So if I could try to put it into perspective, it would somewhat go in that direction. So this is NB. And then for the ball and socket, let me just erase this guy because we don't need it anymore. For the ball and socket, that's when you need a little bit more knowledge of what ball and socket would be. So ball and socket is just, it's going to be some sort of cup and a ball inside, and this cup is going to hold the ball, but it's going to allow this ball to rotate in every single possible direction. So it's going to hug the sphere. In other words, it's going to restrict a reaction in the X. It will create a reaction in the Z, and it will also have, well, X is this way, my bad, and it will also have a reaction in the Y direction. And but it's going to allow rotation everywhere. It can freely just move around. Obviously, if you move it too much, you're going to have some geometric constraints. But as far as what we're concerned with, it should be able to rotate in every direction. In other words, there's no mz, mx, my, and mz reactions. So no moment reactions at A. Okay, so with that said, we're gonna have I'm gonna draw it in the positive direction just for convenience. I'll call it RZ, and then we have RX, and then obviously RY. Okay, so how many unknowns do we have? Essentially, we have 5. I did say we were going to exhaust the equations. Yeah, we're going to pretty much exhaust them. We're going to do 5 equations, leaving one of them to not be used. Okay, so how about we just, dive in and let's do it. There are a couple different ways to approach this problem. I personally prefer in a complex problem like this to build all the equations. So do sum of the forces, sum of the moments, every direction, and then jump into building a matrix and just letting the computer or your calculator solve it for you. Okay. Oftentimes with those many unknowns, it's just not worth trying to solve one by one. It's possible, but it's just not worth it. Okay. So let's just start with the easy stuff, right? So sum of the forces in the x, I'm going to get, so if I say, well, it's not really to the right, but this direction positive, I'd get that Rx, okay? Remember, NB is also going that way, so plus NB. Anything else in the x direction? Not that I can see. Tension BC is on the YZ plane, so it doesn't have an x component, and that's it. So this is our first equation. Okay. Sum of the forces in the y, we have a positive that way, equals 0. Then obviously Ry. We already accounted for NB. TBC is definitely in the y. There's a component there. And to get to that component, we should probably do a little bit of geometry there. Okay, so we're worried about the y component, which I'm drawing in 2D here for you to see it a little bit easier. So imagine me looking at the YZ plane. Okay, so looking perpendicular to it, I'm going to have a y component going to the left. And to obtain that would be, so negative TBC, and then that would be cosine of this angle theta. So instead of obtaining theta, why don't I just simply plug in the cosine? Actually, probably easier to obtain theta, because we don't, or we can just calculate the hypotenuse. So let me just calculate the hypotenuse real quick. So the hypotenuse should be, so 0.5 squared plus 1 squared, because those are the sides of that triangle right here. If I could show you that. This triangle is a 1 meter by 0.5, so the hypotenuse is 1.12. So I'll get 1 over 1.12. So 1 over 1.12. Okay, so that's the cosine ratio already, and that's another one. Okay, let me just double check. NB is not in that direction, the weight is not, and that's it. So sum of the forces in the z we have equals to 0, up positive. We get obviously RZ minus the weight, which is 20 kilograms times 9.81 gravity, right? We get the weight is going down in the z direction. We have TBC again. In this case, we're worried about the component that's going up, so plus TBC, and in this case we have sine, so 0.5 over 1.12, right? And then one last thing, I think. Let me double check. 1, 2. No, that looks like it. Okay, so third equation. We just need two more, right? So two more equations. Let me think about what kind of equation I would like to play with. Let me see. Typically, I might probably, let me think about this real quick, because I could do it scalarly or I could do it with the matrices, right? For the moments, I think I'm gonna do it with the matrices because it's always a good safety net, right? Doing it scalarly sometimes is not always possible. So let's go the harder route, but it turns out to be the best option for every single scenario, right? So if I take a moment about the x-axis, so positive going, this is kind of like a way to show it, so positive going that way, so my thumb pointing in that direction of the double arrow, rotating like this, right? It's kind of like the notation. So this would be r cross f, right? So we have to literally look at every single possible force, right? So r cross f. So before we even do that, we might want to define some of those vectors, right? Because otherwise it's just going to be extremely complicated. So how about this? I'm going to erase this guy and take my time to define those vectors in 3D. Okay, so defining the reaction R, right, in 3D, if I, let me think about this, how I can, it's just going to be in Cartesian, that would be something like Rxi plus Ryj plus Rzk. Then we have the weight, which is obviously 0I plus 0J minus 20 times 9.81 K. Awesome. So 2 down, and B, we have just NB as its magnitude going in the I direction, 0J plus 0K, and then finally TBC. So TBC is the one that we would use. Obviously, the magnitude times the direction in the I, which is 0. So I should have really, there's no component in the x direction, minus, right, TBC magnitude, what was it, cosine? Yes, 1 over 1.12, cool, J plus TBC 0.5 over 1.12, cool. So now that I define these guys, I just have to define the position vectors. So scroll down a little bit more. So I'm taking the moment about x, but I'm going to define the position vector coming from where all the axes meet, because it's easier for that purpose. Okay, so my position vector, just call this point O, is going to be, so ROA, the way that I would define it, so it's just, let me think about this real quick. It's kind of trying to warm up my brain real quick. So in the x direction, we just have 1.5, so it's 1.5 I, nothing in the j, and nothing in the k, correct? Correct. So so the next one is gonna be RO, I don't know what to call this point here. Let's just say this is point F, right? So ROF, right? ROF, and this is where it gets a little bit tricky. We're halfway on the rod, which makes us halfway on this 1 meter mark and halfway on this 1.5 meter mark and halfway on the 2 meter mark height. Okay, so that's the trick there. So we are gonna get that point, that position vector places us at 0.5 I. Let me see, plus 0. No, I apologize. 0.75. Read it wrong. Be very careful with these. They can be kind of tricky. I'm kind of doing them all at once. Plus 0. So yeah, 0.75 I plus, and this is the 0.5 J plus 1K. Awesome. And this last position vector can be applied for both NB and TBC, so that's convenient. So ROB is going to be 0 I, there's no component, it's against the wall, plus, what do we have, 0.5? No, it's complete, it's a 1, it's a 1. We're not halfway anymore. So 1J, correct, plus 2K hat. Awesome. So with that, those created, it's a lot easier actually. In fact, I can do, if I do, I could even do a little bit of a shortcut. And now that I'm thinking about it, that may be one of the best ways to approach this guy. Let me think about this and how I can present it to you. So if I do, so some of the moments, if I do some of the moments about O, which is the point that I defined that intersects every single one of those axes, and I do that equals to 0, when I actually do, for instance, ROA cross R vector, which is just, our x, our y, and our z components, plus ROF cross the weight, plus ROB cross T, plus ROB again cross NB. The interesting thing is, because the point O is part of every single one of those axes, when I do this calculation and I do all 4 cross products, add them all up component by component, the answer of each I, J, K, so each of those answers is actually, and I should really, I'm missing some stuff. Plus M, that's what I'm missing, plus M. Okay, now that I was thinking about it, let me go back and kind of rephrase myself. So this is gonna be a moment vector. Okay, now that makes a lot of sense. So, okay, so let me try to explain this to you guys. So the way that I'm doing this is a little bit of a shortcut, which turns out to be one of the quickest ways to obtain those type of answers, right? If I was focusing on a certain axis, which I'm not, right? I want moment, no, I don't have a moment reaction there. So I was right. That's why that doesn't make any sense. Okay. let me think about this, guys. I'm so sorry. I really need to stop and think about this before I... Yeah, okay, so in this case it doesn't apply. Alright, as always, doing all the problems on the fly, trying to, show you how I can, I think about these, because a lot of times certain problems will require different approaches. Okay, so in this case, I'm so sorry. I do need to do them separately. Otherwise, I'll never be able to solve this problem. It's just going to be too crazy of a, algebra process. So some of the moments about the x-axis, when I do these guys, I'm just going to add the x components of my answer, right, to all those cross products. And when I do that, that's going to give me an equation. So another equation. When I do this again, just to, by adding up the j hats from all those cross products, I'm going to get another equation. And it turns out that those are enough for me to solve the problem because I have 5 unknowns. Technically, if I wanted to verify my answer, I could do some of the moments about the z-axis, and with the answers that I have, do it all again, add all the k-hats, I should get an answer of 0. And that's how I can triple check my answer, right? I'm not going to do that, or maybe I can at the end if it's not too long of a video. But yeah, so essentially what you have to do, so let's just I guess do it, right? Because it's easier to, it's easier if you see me doing it. And let me zoom out here a little bit so that it becomes easier for you to see. Let me see if I can make this, yeah, so let me zoom out a little bit more. I'm not sure if, I think if you're in full screen, you can still see my work. Okay, so setting up those cross products, I'm going to be able to add them in the x, the y, and the z direction, and use that with the sum of the forces that I did to come up with the 5 unknowns that the problem is asking. Okay, so let's do that. So ROA cross R. So ROA cross R. I, J, K. Then we have ROA, which is 1.5, 0, 0. Then R, which is Rx, Ry, Rz, plus the next guy. And I already know that this is 0, 0. And then let me just do the math here real quick. I'm tired of just 196.8.2 negative. That's the weight there. And then ROF was 0.75. Terrible handwriting, I'm sorry. 0.5. Then 1. Again, I, J, K plus I, J, K. And then again, I'm just on the tension there. ROB was 0, 1, 2. And this guy was, I have a 0 here, minus 1 over 1.12, 0.89. I could even do this at the outside. Multiply by t at the outside. So 1 over 1.12, I'll do it like that for better accuracy. And then 0.5 plus, so remember the t is going to get multiplied everywhere. So that's the magnitude. And I should have called it TBC. Doesn't really matter. It's the only tension. So again, last one. NB is the same position vector, 0, 1, 2. And then we have NB as NB. Apologize. It should have been NB there. Just the magnitude. I could have put a 1 and just multiplied it again. It's really doesn't really matter. And then I, J, K. Okay, cool. So I have 1, 2, 3, 4, 1, 2, 3, 4. These guys should add up to 0. So if I do the cross products and I add up the I and J components, I should get the other 2 equations that I need. So cross product of I, and adding it all up. So cover the I column and multiply the other ones. I get 0 plus 0.5 times negative 1.96. I'm sorry, 196.2. And plus, well, minus 0, right? So because it's minus 1 times 0 is 0, I'm just going to skip that. Plus 1 times, so it's 0.5 over 1.12 times 1 minus 1 over 1.12 times 2. And then this guy is just 1 times 0 minus 2 times 0, that's 0. So that's my other equation. And really, I should have kept the TBC. So big mistake there. I can put it right now. TBC. Cool. So, and that one's pretty easy actually. I should be able to actually just grab that unknown if I wanted to. I might, instead of doing it in the calculator, in the Excel or solver. I might do that in a second. J, so to do the J's, we just cover the J and then we just worry about the other ones. So 1.5 times RZ, the other one is just 0. Cover this guy, this is 0.75 plus 0.75 times negative 1.196.2 minus 0. Next one, we have 0 again, so I'm not going to write it. And then finally we have 0 times 0, 2 times NB, so minus 2 times NB equals 0. Two unknowns there, so not quite convenient. Let me see. Can I do the? I'll just do the K hat. Why not? Right? We don't really need it to solve it, but maybe it's easier. Maybe it will give us an unknown right away. So let's see. We would have 1.5 times RY. This guy would be 0. So plus, so the second matrix is cross product is 0. Right? 0.75. Nope. No, yeah, 0. 0.75 times 0, minus 0.5 times 0. The third one is gonna give us, let's see. It's gonna give us 0 again. And the last one, let me see. Last one is gonna give us plus NB. Not sure how that helps. Or minus NB. Yeah, minus equals 0. Let me double check. So 1.5 times RY minus 0 RX. 0.75 times 0 minus 0.5. And let me just, get a highlighter here. So I'm right here. 0.75, 0, 0.5 minus 0.5 times 0. That's 0. This times that. Yeah, so I missed that guy. So that's what was weird about it. I was like, okay, so this times that. Oh, that's 0. Yeah, 0 times that, 0. Minus 1 times 0 is 0. Yep. And last one, 0 times this. Minus this times that. Yep, that's right. Okay, so yeah, it doesn't seem like it helps. Still two unknowns there. Let's see. Let me see if I can just get TBC from this equation. Let's just obtain that, and let's see what we can later obtain from the other equations. So that would be, if I move it to the other side, I'd get minus 2 times 1 over 1.12, right, moving it to the other side, plus 0.5 times 196.2, correct? And this is all divided by, well, I could say multiplied by 0.5 divided by 1.12. Correct? I think so. And we get that TBC is equals to 43 newtons. Let me double check this answer before I move on, just to make sure. that we're on the right track before I move on. I'm getting slightly different answer, maybe because it was used a different one quick second before I move on here. Let me just double check something. Did I okay, so I think I've spotted my mistake. I'm not even sure where I obtained that okay, so the 1.12, yeah, so yeah, the 1.12 was 1 over 1.12. That makes sense though. Because the 1.12 was the, oh, I really should have taken the square root of that. No, I did. So 1 squared, square root of 1 squared plus 0.5 squared. Yeah, 1.12. Could be just a rounding because we're so close, 1.18. Let me see this. If I use slightly more in really, okay, I think I've spotted the mistake. So on the I hat, where did I get those values from? Okay, I think I've spotted the mistake. So let me just use a different highlighter. We're getting, so this should be correct. This should be correct. This also should be correct. However, here on this multiplication, I'm getting, I don't know where I got this from when I was doing this. I think I may have just overlooked something. Yeah, I'm not even sure where this came from. Let me see this. So for this I do this times, oops, too dark. I do this times this. Okay, so that's it. Okay, big mistake, guys. Big mistake. Huge mistake. So these are all part of the same cross product, right? So it's this times that minus this times that, and then you multiply by TBC, right? So really, I think that's the problem. I kept it outside and kept thinking I was, already including the unknown, but okay. So let me redo the calculation real fast. So I get 0.5 times 196.2, and this whole thing is divided by plus. All right, I think that makes a lot more sense. Yep, that's the correct value. Okay, so I apologize for that. And as you can see, a lot of times when you're in a hurry and you're trying to just get the answer, you really have to, make sure you're taking your time when you're solving these. Okay, so lesson learned for us. TBC is equals to 43.95. Not too much off, but definitely enough that it can cause us some problems. Newtons. Okay. All right, that looks awesome. So now that I got this, let me just, yeah, okay. So now that I got this guy, that's one unknown that I already figured out. Let me look for other equations that have that I may be able to get an answer from. So it looks like some of the forces in the y and some of the forces in the z are great candidates. So I can do TBC times that and get our y. So our y is just simply going to be, if I calculate it, 39.24 newtons. And then RZ becomes a little bit more complex, but that's fine. and then plus 20 times 9.81, 176.6 newtons. Cool. And with this, I should be able to go back to one of those two and get a couple answers. So let's do this guy. So I just calculated RZ. So if I do this times negative 1.5 plus 0.75 times 196.2, and all that divided by negative 2, I get that NB is equals to 58.86, leaving only one unknown left. And let me double check all those just to make sure. So yep, perfect. We're good. Now let me see the last one. I think I'm only missing Rx, which is just the opposite of NB, right? So Rx is negative of NB, so 58.86 newtons. And that covers it. Let me just see what they wanted. So they wanted the components of the reaction. So these are the components, NB and the tension, and that's it. So just to write it all together, TBC 43.95, and as we already said, NB 58.86 newtons. Awesome stuff. Very cool. So let me just go back here so you can have those in case you're still working on it. And that's it. So just a quick recap as to why this problem was really interesting. We were dealing with 5 unknowns, 3 coming from the ball socket, which is only supporting force reactions, not moment reactions. Okay, it's allowed to rotate everywhere. It's a sphere. You can rotate freely everywhere. I mean, it should have some geometry constraints, obviously, but we're not worried about that. We're assuming that we're way above those constraints and it's not gonna, hit anything. The wall has a reaction that's normal to it. Then we also have the cable, and the cable is always in tension. So through the geometry, we can figure out those answers. And just one last thing, I think you already caught the answers there. When doing the cross product, right, the cross product allows us to actually, if we wanted to get all those answers at once, we could. All you have to do is just perform the cross product for all those components, and you're going to get, when you plug it in a calculator, for instance, you would get those results just, as the same way as you would by summing the i's, the j's, and the k's. I just wanted to show you it like that because I think that's the best way to show this. But it's all in one equation, which really is this set of cross products, right? So through this set of cross products, you get the other equations that you need, right? And you can actually pick and choose in this case because we have 5 unknowns and 6 equations to work with. So I could have done IJ I could have done IK or JK instead of just IJ like I did. Okay, so just to clarify that. And that's it, guys. Hope you enjoyed it. And if you have any questions, just let me know, and any suggestions as well. And I'll catch you in the next one. Take it easy. Bye-bye.